Okay, so in this example, we're going to be taking a look at the electric field inside and outside a uniformly charged sphere. And the sphere is an insulator, and that's important because uniformly charged means we're talking about the charges themselves being distributed throughout the volume of the sphere. Now, the sphere is going to have a radius of capital R, and our Gaussian surface, our Gaussian sphere, is going to have a radius of little r. And this is going to be very, very important here in just a couple of minutes. We've got two parts to this problem. The first part is outside, and that's the easy part. Outside a sphere, the electric field is going to look like that of a point charge, and so E is just equal to kq over r squared, where this q is the total enclosed charge, or the total charge of our sphere. And this r happens to be any radius where r is greater than capital R. Now, the trickier one to deal with is going to be what's going on inside the sphere. So now we're trying to find E for when little r is less than capital R. So the first thing we're going to do is write Gauss's law, and that's going to be the integral of E dot dA is equal to Q enclosed over epsilon naught. Now, as is typical, we have a uniform electric field everywhere at a distance little r from the center, and that dA is just going to, the integral of dA becomes the area, the surface area of a sphere. So we end up with E times 4 pi little r squared, because that's the Gaussian surface, is equal to Q enclosed over epsilon naught. And now the tricky part, the part we have to really be careful with, is Q enclosed, because the amount of charge enclosed varies as the size of our Gaussian surface changes. All right, so the further inside you get, the less charge you have enclosed. So we cannot treat this any longer as a constant. And to deal with this, we're going to have to use charge density. So we know that Q enclosed is going to be equal to the volume charge density rho times the volume enclosed. So the volume enclosed is pretty simple. That's going to be the volume of a sphere, where the sphere happens to be the Gaussian sphere. So the volume enclosed is equal to 4/3 pi little r cubed. Now rho, by definition, is equal to the total charge divided by the total volume. So we have the total charge, which is a constant, divided by the volume is going to be 4/3 pi capital R cubed. So putting this all together, what we get is Q enclosed is equal to capital Q over 4/3 pi capital R cubed times 4/3 pi little r cubed. So we can cancel out 4/3 pi, and Q enclosed becomes Q little r cubed over capital R cubed. So E times 4 pi little r squared is equal to capital Q little r cubed over capital R cubed epsilon naught. So now we'll cancel out the r squared with 2 of those r cubes in the numerator there. And we're going to get E is equal to q little r over 4 pi epsilon naught capital R cubed. And that is the final answer. That's the field model for when you're inside this sphere. Now, we can see two things. If we graph this, we want to know what is the electric field with respect to the radius. Electric field versus radius. Up here, we're going to have the maximum electric field. And right here, we're going to have the radius of the sphere itself. So we're going to go from the exact middle of the sphere out to the outer edge of the sphere, and then from the outer edge of the sphere into infinity. So what we can see is that when E is less than R, less than or equal to capital R, when little r is less than or equal to capital R, we can see that E is just proportional to R. So it's going to be a straight line. When R is greater than capital R, then we're going to have E as being proportional to 1 over R squared. So that makes it easy to construct our graph. We're going to have a linear graph all the way up to the maximum till we get to the outer edge of our sphere, and then it's going to drop off as 1 over R squared. Let's try that again. There we go. And so we could say here that E is proportional to 1 over R squared, and here we get E is directly proportional to R.